Let's first write down our proposition in terms of Pn. As for Pn, on the left hand side, I'm going to rewrite it into a summation notation, which is summing from R starting from 1 to n of, using this as a hint, it is R of R plus 2 and R plus 5. And on the right hand side is this that is given to us by the question. So this 3n squared plus 31n plus 74. And we also need a range of values for n, and since the smallest possible n can go is 1, so n is going to be all positive integers. I'm going to go for the smallest possible n, which is 1. So I'm going to look at P1. On the left hand side of P1, we have summing from R starting from 1 to 1 of R, R plus 2 and R plus 5. There's only one term, and that is when R is equal to 1. So 1, 1 plus 2 and 1 plus 5. This is giving us an 18. And on the right hand side of P1, it is this, but n is replaced by 1. So it's 1 over 12, 1, 1 plus 1, 3 plus 31 plus 74. And this is also equal to 18. That is why we have sort of like proven that P1 is true. And since we have proven that P1 is true, we are going to make an assumption. I'm going to assume that Pk is true. And for some k, that is also a positive integer, which means that I'm assuming that if I was to sum from R is equal to 1 to k of R, R plus 2 and R plus 5, this is going to be equal to 1 over 12 of k, k plus 1 and 3k squared plus 31k plus 74. And what is our aim? My objective here is to prove that pk plus 1 can also be true. So if I were to have this as the aim, that means I'm trying to show that when I sum from R is equal to 1 to k plus 1 of R, R plus 2 and R plus 5, this is 1 over 12 of k plus 1, I replace all the n by k plus 1, of k plus 1 plus 1, and 3 times of k plus 1 square, replacing n by k plus 1 plus 74. That means I'm looking at this as 1 over 12 of k plus 1, k plus 2, and if I were to expand this, this is equal to 3k squared plus 37k plus 108. We are supposed to prove this over here. And I'm going to try to start with the left hand side, which is the summation from R is equal to 1 to k plus 1 of R, R plus 2 and R plus 5. And you know what is this? This is when R is equal to 1 plus when R is equal to 2 plus all the way until when R is equal to k, and then the last term is when R is equal to k plus 1. So we can actually break this up into two parts, summing from R is equal to 1 all the way until one term that is before this, which is when R is equal to k of R, R plus 2, R plus 5, which means that I have that very last term, that is when R is equal to k plus 1. So replacing all the R by k plus 1, it is k plus 1, then k plus 1 plus 2, then k plus 1 plus 5. Which means that what I have now is this, which I've already assumed that it is true, so I'm going to replace it with 1 over 12 of k, k plus 1, 3k squared plus 31k plus 74. Plus this is going to be k plus 1, k plus 3 and k plus 6. And since what we are trying to show has a form that is like this, it has 1 over 12 and k plus 1 here, so I am going to factorize out 1 over 12 and k plus 1. So 1 over 12 and k plus 1, that means what I'm going to be left with inside for this expression is k multiplied by this, which is 3k cubed plus 31k squared plus 74. As for this, since I factorize out 1 over 12k plus 1, so this will disappear and I need a 12, so 1 over 12 times 12 is 1, and then what I'll be left with is just this times this, and this times this is k squared plus 9k plus 18. And if I were to expand this further, what I have here is going to be equal to 3k cubed plus 43k square plus 182k plus 216. And if I were to look at just this expression here and I press this into my calculator, attempting to find the roots of this, we will be getting one of the root as a minus 2, which means that one of the factors of this is going to be k plus 2. So this is 1 over 12 of k plus 1 and k plus 2 and another factor over here, which I can actually find by using the process of long division. So this plus 43k squared plus 182k plus 216. And I will divide this by k plus 2. This is going to be 3k squared here. So here is going to be 3k cubed plus 6k squared. I'm going to have a 37k squared plus 182k. So plus 37k. This is 37k squared plus 74k. If I were to minus this, I will be getting a 108k plus 216. So here is going to be plus 108. So here will be 108k. This times this is 216. So I'm expecting a 0 as my remainder anyway, since I'm dividing this by its own factor. Which means that here is 3k squared plus 37k plus 108, which is actually the same as what we are trying to prove over there. That is why now what we have sort of like proven is that the proposition of pk plus 1 is going to be true, as long as we have made use of the fact that pk is already true, which means that I can say that pk plus 1 is true if pk is true. And with this that we have just proven, and since p1 is true, what we can say is that if p1 is true, that means p2 is going to be true, because every time when pk is true, the next term, which is the next proposition, which is pk plus 1 is true. So when p1 is true, p2 is going to be true. When p2 is true, p3 is going to be true, which means that for the entire pn, when n is all positive integer, it is going to be true. This is mathematical induction. We are going to give a conclusion based on this. So since p1 is true, by the process of mathematical induction, we can say that Pn will also be true for n to be all positive integers.